Okay, we're going to finish up these introductory videos to the derivative by looking at the relationship between continuity and differentiability. And I'm going to start by proving this theorem. It tells us that if a function f of x is differentiable at a point x equals c, then it's also continuous at x equals c. Okay? So how do you prove something like this? Well, we're going to assume that it's differentiable at c. Okay? So we start here by, let's assume f of x is differentiable at x equals c. Well, let's just remind ourselves what that means. And so I'm going to use the alternative derivative, or the alternative definition to the derivative. And so this means that that f prime at c is equal to the limit as x approaches c of f of x minus f of c divided by x minus c. So it means that this is equal to this limit, and so this limit exists and is equal to a finite value. Okay, so I could say, so this limit exists and equals a finite value. Okay, so this limit here exists, it's equal to a finite value. So we want to show that it's continuous. We want to show f prime of x is continuous at x equals c, which means that the limit as x approaches c of f of x is going to be equal to f of c. So that was our definition of continuity. In other words, the limit of the function as it approaches c is equal to the value of the function at c. Okay? So I'm going to use this limit here somehow to show that this limit here exists. Okay? Now, let me tell you, this wouldn't be at all obvious. Okay? You wouldn't have necessarily figured this out on your own right away. Doing proofs like this just takes a lot of exposure and experience, and you have to see different proofs and the ways that it's done before you really get good at learning this sort of thing. So don't feel bad like when you see this and you're like, oh, how would have I ever got it? Well, if you like math enough and you want to learn how to prove things over time, you learn more and more and more, and you gain the ability to do that. Okay? But let me show you how we're going to do this. Okay? So first of all, I'm going to just say f of x here is actually equal to f of x minus f of c plus f of c. And all I've done here is I've subtracted and added the same thing. So if I combine these, they cancel out, and of course I'm just left with f of x. Okay? But the reason that I'm doing this is I want to try to build this this difference quotient inside here. So I'm going to need this x minus c on the bottom. So what I'm going to do here is I'm going to say we'll take f of x minus f of c, and then I'm going to multiply this by x minus c over x minus c plus f of c. And see, by doing this, I'm just multiplying this by 1, and again, that doesn't change anything. This is just 1 multiplied by this would give me f of c. These two would cancel out, and I'd be left with that. Okay? But now what I can do is I can rewrite this, that f of x is equal to the following. I'm just going to bring that over there. f of x minus f of c over x minus c times x minus c plus f of c. Okay? And so, again, so this is equal to that. So now, what I want to do is I want to show the limit of f of x is equal to this. Okay? So then that means the limit, I'm going to take the limit of both sides. If this is equal to this, then the limit of that will equal the limit of this. Okay? So the limit as x approaches c of f of x is equal to the limit as x approaches c of f of x minus f of c over x minus c, and then this is going to be x minus c plus f of c. Okay, well, let's simplify this. So this can be distributed over both of those. Okay, so and maybe I'll just talk through this. So if I distribute it over this one, then what I can do is I can take the limit of this and the limit of that. So the limit of a product of two functions is the product of the two limits of the functions. But the limit of this, that's just the definition of the derivative. So this would just be equal to f prime at c. And the limit of this as you approach c is just 0. So this would be times 0. And then this is the limit of f of c as x approaches c. Well, f of c is just a constant. And so the constant is always just equal to itself. So this would be plus f of c. Okay? So now since f prime of c is a finite value, any finite value times 0 is just 0. So this whole thing is just equal to f of c. And so what I've just shown is that the limit as x approaches c of f of x is equal to f of c. Therefore, f of x is continuous at x equals c. Okay, so I assume that it was differentiable, meaning that the derivative, the limit here existed, and because that limit existed and is a finite value, then I get this whole thing, this limit, to equal f of c, and that just means that it's continuous at c. Okay, so that's the way that this proof works. It's a neat little proof. Not at all obvious, but definitely true. And so what you get here is that differentiability is this sufficient condition to ensure that the function is continuous. So let's see if I can say this. So if it's differentiable at a point, it will be continuous at a point. So let's write some things here and show some pictures. If f of x is differentiable at x equals c, then it will also be continuous at x equals c. Okay? Now, this isn't true the other way around. This is where in math, these if-then statements are very important. They go one direction, but they don't necessarily go the other direction. So I can't say that if it's continuous at c, then it's going to be differentiable at c. Okay? It doesn't necessarily go the other direction, and I'll show you that in a second. But what this does say, that if it's not continuous, if f of x is not continuous at x equals c, then it's not differentiable there. Because if it were differentiable, it would be continuous, right? Then f of x is not differentiable at x equals c. Okay? So in other words, you know if a function's not continuous at a point, then it's not differentiable there. Okay? It has to be continuous in order to be differentiable. But being continuous is not enough. So let's write that down. But being continuous is not enough. And I want to say guarantee, but I don't know how to spell guarantee. I always mess it up. Is not enough to, I'm just going to spell it. Guarantee. I don't think that's right at all. But to guarantee that it will be differentiable. So being continuous is not enough. Okay? So in other words, maybe I can even, so it, let me just write this. It can be continuous at a point and still not be differentiable there at the point. Okay, so I got like 3 different statements that this thing implies that really helps us understand the idea of differentiability. Okay, so basically, if this is the first one is the theorem. If it's differentiable at C, it's also going to be continuous there. Okay, and that means if it's not continuous, then it's not differentiable at C. But you can't flip it around. Just being continuous is not enough to guarantee that it'll be differentiable. Okay, it can be continuous at a point and still not be differentiable at that point. So let me just draw a few pictures to help illustrate some of this. Okay, so the idea of differentiability is that you have this smooth, unbroken curve. So kind of think like a polynomial function. Okay, it's this smooth, unbroken curve. Okay, or think of the sine wave. It's smooth, just going up and down. Okay, but something like the absolute value, okay, something like that, okay, where you have a sharp turn. It's continuous here. The limit is equal to the value of the function at that point. It's approaching 0, and the value of the function is 0. So it's continuous at 0, but it's not differentiable there. Okay, so if you have a sharp turn. So another example might be, let's say you have maybe a function that goes up like this and then goes like that, right? So here you got these slopes that are going like this, and then suddenly they change into these negative slopes that are going down like this. So at that point where it changes from these steep positive slopes to these negative slopes, okay, it makes that instantaneous change. And so the derivative does not exist at that point. Okay? So in other words, these things have to be, smoothly, each point here, okay, at each point this tangent line is just a little more steeper or less steeper than the point before it. And it does that in a continuous way. It goes through every possible value. The slopes go through every possible value as it goes around that curve. Here it's like really steep, and then instantly it goes the other way. So any type of sharp point or cusp like that, it's not going to be differentiable there. It's continuous at both of those points, but it's not differentiable. A differentiable curve will be the smooth curve, and the rates of change pass through all the possible values for that rate of change as it goes from point to point on the curve. Okay? So then some other ways that it might not be differentiable. Anytime it's not continuous. So if you just had a hole in the function for whatever reason, okay, it will not be differentiable there. Okay. Now, in this case, it approaches a limit there, so you could define the function at that point. In other words, that's a removable discontinuity, and then it would be differentiable there, but you would have to make sure to define it at that point. Or if you had, let's say you had it defined at another point here, okay, then again, this is not continuous, it would not be differentiable, but if I moved the point down there, filled in the hole, then it would be continuous. And I actually like, there's a picture that your book has of some of these examples. Let's see if I can find it. And it's actually, what these examples are doing is it's trying to show you the secant lines. So like these are like different points on the curve, and if you do the secant line between this point and that point, you can see that these secant lines are not converging onto a tangent point. So in other words, where is it? Like here's a hole in the graph here. If you see that, there's this hole in the graph, and the graph is defined to be up here. Well, all these secant lines, you got these infinite number of secant lines, they're not converging into a tangent line. Okay? So here, when it oscillates like this forever, okay, in that case, if it oscillates forever like that, you can't have a derivative. It's actually, the limit doesn't exist at that point, and so it's not continuous at that point, which means it can't have a derivative. And then if the graph here has a hole, so it's defined to be that point, and then it's showing how the secant lines are not converging. So anytime there's a jump here in the graph, right, anytime, you know, if your graph maybe has a point here, and there's a jump there, it's not continuous, it's not differentiable at that point. Other possibilities might be, you know, like y equals 1 over x, right? It has this vertical asymptote, it's not continuous at that point, and so it's not going to have a derivative at that point. One other one, which is less clear, is this is actually going to be the graph of y equals the cubed root of x. Okay, so if you flipped it around, it would be like this. Y equals x cubed. This would be continuous. This would be differentiable at every point, and it would have a horizontal tangent line here, right? Okay, but then when you do the inverse of it, you rotate it around the line y equals x, and you get this. Okay, this, what was the horizontal tangent line here, is a vertical tangent line, right? And this is not differentiable if it has a vertical tangent line. So not differentiable at x equals 0. And the reason is that that limit doesn't exist. That limit actually is equal to infinity, right? You have this infinite, you have an infinite limit, but it has to be a finite value for it to be differentiable. This one is kind of weird because it is differentiable at every point, and this is the same graph, basically. So you think it should be differentiable at every point, but not when this you get a vertical tangent line. And to maybe motivate you why this would be the case is notice this theorem would not have worked, right? Because at this point here, I had to rely on the fact that when I took this limit, I got a finite value. Remember? I said, so this limit exists and it equals a finite value. If this were infinity, then this product wouldn't necessarily go to 0, and I couldn't say that it was continuous there. So one reason the infinite, the the vertical tangent line is not allowed is that you use that finite property in theorems when you want to state things about differentiable functions. Okay, so a function is basically, the simple idea is if you have the smooth, unbroken curves that aren't taking any sharp turns, right, then it's differentiable, and you get this fading of one tangent line. Okay, the slopes, it basically, as you go from one place on the graph to the other place on the graph, and you have these two different slopes, from here to here, it's actually passing, the slopes are passing through every possible value from this slope to this slope, kind of like an intermediate value theorem, but with slopes, right? So in fact, when you take the derivative here, if it's differentiable at every point, then the derivative is also differentiable at every point. It's also, the derivative is, I shouldn't say the derivative is differentiable at every point, but the derivative is continuous at every point. Okay, so a good picture of this would be these examples that I showed. So this thing is a nice smooth curve. Well, this is an unbroken. It's continuous at every point, right? But this one, okay, at these places where it takes a sharp turn, this graph jumps. It's not continuous, okay? And so these are some deeper things about the derivative. They help you understand the idea of differentiability and its relationship to continuity and things like that. And in particular, the relationship is if it is differentiable, it will be continuous. But to be continuous, like the absolute value function, it is continuous at 0, but it takes a sharp turn, and so it's not differentiable there. So being continuous is not enough to ensure that it's differentiable. Okay, differentiability is more than that. Okay, but if it is differentiable, it will be continuous there.